This video is on equipotential surfaces. An equipotential surface, sometimes we shorten it to just equipotential, is a surface, often imaginary, every point on which has the same electric potential V. In order to move a charge from any one point on a given equipotential to another on the same equipotential, the electric force will do zero work. But to move any charge from one equipotential to a different one, the electric force will do some amount of work. It might be positive, it might be negative, it depends on what we're doing, but definitely some amount of work. Two examples of equipotential surfaces are the plates of a charged capacitor and a conductor in electrostatic equilibrium. This entire conductor has the same electric potential V. We might say that the conductor is an equipotential volume. Instead of just a surface, it's a volume that has the same electric potential. At every point, equipotentials are always oriented perpendicular. How about I write that symbol instead of writing out the word? To electric field lines. Closely spaced equipotentials indicate regions where the electric field is strong. Widely spaced equipotentials indicate regions where the electric field is weak. If you recall the equation, we ran into it first with capacitors, that the voltage difference between the plates of a charged capacitor is equal to E times the separation of the plates. If there's a certain voltage difference here, let's say it's 10 volts between equipotentials, so that number is fixed. You can see here that if this number, if that's a small number, if those equipotentials are very close together, then that means that in general the electric field there must be big, and vice versa. If the equipotentials are spaced far apart, in other words, D is big, then the electric field is a smaller number. So that's what we're trying to say here. Closely spaced equipotentials indicate regions where the electric field is strong. Widely spaced equipotentials indicate regions where the electric field is weak. Here we have four charges, two positive and two negative, and I've drawn in the electric field lines, or some of them, already. And what would the equipotentials look like? Well, the equipotentials are at right angles to each of these. So the one equipotential around this charge might look like that. Another one might look like that. And we can draw in a few more here. These are not supposed to be concentric circles. They kind of balloon out a little bit bigger on the outside of this series of charges. And of course, we can't draw them all in, but we can draw in a few. There are some equipotential surfaces. Each of these is a three-dimensional thing. So this is maybe not exactly a sphere, but it's some sort of sphere-like shape. And the potential at every point on that sphere right there, every point on that sphere right there, etc., is equal to all the others. In fact, for this one that I'm pointing at here near the middle of the screen at the bottom, this potential will be negative, and it will be fairly large because it's pretty close to this negative charge. This one will also be negative, but it will be smaller. If we do two similar things up here, this equipotential will have a large value of V. I'll make that V kind of big. But this one out here will also be positive, but it's going to be less. In fact, I hope you can see that right there in the center, the potential will be exactly zero due to symmetry constraints. Within a field of potential, electric field lines point from more positive toward more negative potential values. That is, electric field lines point from the more positive equipotentials towards the more negative. So if we have some equipotential surfaces, and let's just say that that's what the potential is for each of these, the electric field lines are going to point in this direction here, from more positive towards more negative. And positive charges are going to be forced in that direction. If we have a positive charge and we let it go, it's going to tend to move to the left on our number line here. And if we have a negative charge, it's going to tend to move to the right. Let's finish up with a little bit of a practical problem here. Which points have the highest and lowest potentials? And give us some sort of justification for that. Well, of these 5 points, N has the highest potential and J has the lowest. And we know that because the electric field lines are always drawn from higher toward lower potentials. Let's take the same picture and suppose that there are 3 values of potential that can be assigned to these points. Which points have which potential? We said that N has the highest potential. So if those are the 3 values, N is at 200 volts, J is at 100 volts, and the other 3 are all at 150. Part C, draw 3 lines to indicate equipotential surfaces. There's an equipotential surface right there. There's an equipotential surface right there. There's an equipotential surface right there. And this one has a voltage of 200 volts. This one here has 150, according to our problem. And this one here has 100. If we held an electron at point L, so right in the middle there, and we let it go, it would spontaneously move toward which point? And let's justify this in 2 different ways. That electron is going to move towards point N. One reason is that electrons are forced opposite electric field lines. And the other reason is that electrons are forced from more negative potentials toward more positive. And that's the case here. Point L has 150 volts and point N has a potential of 200. Negativer to positiver. That's how a negative charge is going to be forced. All right, let's finish up here. When the 1 electron is released from point L, we said it's going to travel in this direction here. What type of energy is lost? Well, potential energy. And what type of energy is gained? Kinetic. This electron is going to speed up. And how many electron volts of energy is this? Usually we think of energy in terms of joules, but if we're moving electrons between potentials, the electron volts is going to be 1 electron multiplied by however many volts difference this is. And if you remember from the previous page, there were 50 volts difference in between N and L. So the number of electron volts of energy, 50 electron volts. We could convert that into joules, but it's convenient here to just represent it as electron volts.